All right, I think we can go ahead and get started. So welcome everybody to today's webinar on the H2Os Prize. We're super eager to have you here and to share more about the prize. Clayton, if you want to go to the next slide, I can just kind of give an overview of the agenda items and some housekeeping things. So if today's webinar is being recorded, so some of this information will be available after the fact. And also, if everyone could just stay muted throughout the presentation, that would be awesome. We will open it up to a questions session after the slides are over. So yeah, just stay muted while the presenters are speaking. That would be awesome. And then just an overview of what we'll be looking at today. So just an intro to working with the U.S. Department of Energy, Water Power Technologies Office, an overview of the H2Os Prize itself, the technology development goals that the prize aims to achieve, prize phases and awards, and then just some information about the submission package and scoring criteria. And with that, I will hand it over to Katie Jackson at the Water Power Technologies Office to get us started.
Thanks, Brittany. I'm Katie Jackson. I'm an engineer and a technology manager at the Water Power Technologies Office at the DOE. We're a pretty broad office. We have a lot of research, development, and testing going on a variety of emerging technologies related to advancing marine energy and hydropower and pump storage hydropower to make sure there's a flexible and reliable grid. We invest in early stage R&D to try and harness any energy that can be captured sustainably and address environmental issues. We also support efforts to validate the performance and grid reliability for these new technologies, as well as develop and increase accessibility to testing infrastructure and looking at system level opportunities and risk. WPTO generally aggregates, analyzes, and disseminates what we see as relative and objective technical information for all water power technologies and try to make sure our stakeholders are aware of what we're working on and then informing decision makers so that they can make proper decisions related to incorporating marine, hydropower, and pump storage in their systems. This prize itself is part of our HydroWires initiative. So on the hydropower side of the office, we have the Hydropower and Water Innovation for Resilient Electric Systems initiative. It includes all of our grid work in the hydropower program. That includes pump storage, hydropower, hybrids, grid flexibility, understanding the value of some of these opportunities. So this research initiative that launched in 2019, it aims to understand, enable, and improve hydropower's contributions to reliability, resilience, integration in a rapidly evolving electricity system. So we're really excited to be dabbling in our first data prize on the hydropower side and thinking how we can fully utilize the assets we already have while also reflecting and remaining fair to the water system and environmental needs. So I'll go ahead and let the lab team that knows a lot more start explaining the actual prize.
Thanks, Katie. So I'm Clayton Barrows. I'm the PI on this project that has set up and is executing this prize, which is offered under the American-made Water Prize umbrella. And so the goals of the H2Os prize that we have titled it is to support support renewable energy transition by identifying some opportunities for hydropower to better coordinate with power systems. And ultimately we're offering this prize in competition for the total of $75,000 in cash. And so we'll go through some details about why we've structured the prize the way we have, the actual structure of the competition, and then some of the details about what you can expect with submission and scoring on the platform that is hosting the prize. So So starting with hydropower flexibility, which is really the umbrella goal of this particular prize, is how do we access hydropower flexibility and incentivize hydropower to offer their full range of flexibility to the grid, as we recognize that hydropower is one of the most flexible clean power resources on the grid today, and it's likely to become a more important, increasingly important resource as the share of energy that we procure for electricity becomes increasingly uncertain and variable. So the mission statement really here is that winners will develop hydropower scheduling approaches that maximize electricity production capabilities while considering and without violating water management requirements. So we're really trying to incentivize competitors to develop those particular solutions. So in particular, we've thought about this in 3 ways. So first of all, we're trying to incentivize hydropower management performance, and that's kind of trying to make sure that the hydropower scheduling solutions that competitors identify respect the water system's physical and operational constraints. So the goal here is make sure that you are respecting and representing the river basin management and doing a good job of respecting the physical constraints while meeting the physical constraints while trying to meet the management constraints to the best extent possible. And doing that while also providing the greatest benefit to the power system according to the incentives that have been identified, both economic and environmental. And we'll lay out what those are exactly in a few minutes. And finally, we're really hoping that any solutions are novel and scalable and broadly applicable. So really, we're looking for solutions that are not just finely tuned to the problems that we set up for the competition, but also could be applied to larger scale systems and more realistic systems and different conditions. So we really are looking for novel and really flexible techniques. And so we are hoping to incentivize an innovative modeling that will enable hydropower to realize the potential in making sure that we evolve towards more sustainable energy systems. And with that, I'll let Abby talk about some of the water system operational representations in the competition problems.
Great, thanks, Clayton. Hi, I'm Abby Watson. I am with RTI International, and I'm a water resources engineer. And so we've worked with Clayton and his team to, help develop out the competition. So just to, piggyback on what Clayton, just talked through, is part of this competition, we're seeking solutions that adequately represent the water system. We want to make sure any hydropower, production, scheduling solutions are providing feasible hydropower production. And so we're not overestimating how much hydropower a given system can produce. And so in order to do that, we describe, each phase water system by both, describing the physical water system constraints and operational water system constraints. So physical constraints, are actual physical limitations of both the managed and natural parts of the system. So for each problem, we will describe, the reservoirs and hydrogenerator capabilities, with elevation area capacity curves, plant efficiency curves, turbine capacities, outlet capacities. And then also, if applicable, we will describe the river system if needed, if there's river reach constraints or if there's lag and attenuation in the basin, characteristics like that. And then secondly, we will describe, how the water system, the hypothetical competition water system is operated. And so we do that with constraints that represent realistic water system, multi-objective decision-making that water system operators have to think about every day. So in addition to producing hydropower, water system operators have to be, considerate and respect, fish flow requirements or other minimum flows in the system, They want to respect flooding thresholds, meet water demands and other types of, operational constraints. And so these operations are, they can be violated, but they are, it's discouraged to do so in the scoring process, which we'll talk about later. And I do want to note that in the phase 1 competition problem, we did not describe any operational water system constraints. We only described physical water system constraints. And in later phases of the competition, we may have one or more operational constraints, and it may be, we may set up the problem such that an operational constraint must be violated. That could be possible, but it's highly discouraged, and you would want to minimize that. And so the goal of this, competition is to create some kind of logic or solution that sets release decisions given these realistic, operational constraints that water system managers have to think about. And we really want to encourage that, mass balance is obeyed throughout the system. And so that's by following those physical water system constraints, and that, you try as best as possible to meet those operating constraints. So here in the figure, we have an example water system network. And this is more complicated than the phase 1 problem we, described. There's a measured inflow point at the top of the system that feeds reservoir 1. Reservoir 1 is a storage reservoir, so it has some flexibility to operate. And there's hydropower capabilities. There's a flood hazard area below with a flooding threshold, followed by a water diversion demand. And then there's a run of river facility, which means there's not, there's either no or very small amount of storage to operate, but there's hydropower capabilities, followed by another water demand diversion, a fish flow requirement, another measured inflow, and then another reservoir. So as you can see, these systems can be highly complex, which makes this competition pretty interesting. And I'll let Clayton talk more about the water, or the power benefits.
Thanks, Abby. Yeah, so in addition to respecting all the constraints of the water management and the physics of water flow, we are asking competitors to consider the power system operations in this scheduling. So the real goal here is to coordinate with the power system and try and minimize the total system variable cost. So the idea here is to participate in something like an electricity market clearing process, and submit water system energy offers according to the water release schedule that minimize total system operational costs. And that problem considers, in addition to the operational costs, it considers the operational constraints of each unit. So the unit level constraints of turning on and off generating units in the system to meet system demands, and meet the system level constraints like system load balance, nodal power balance, and transmission capacity constraints. And so the idea here is that your water release schedule will be converted to a energy production capability that will be offered to the electricity market that will clear to satisfy all these constraints and create a dispatch schedule for each generator in the system, including the hydropower generators. And so if you can maximize the economic benefit and the environmental benefit of scheduling your hydropower resources, which will impact the schedule of all the other generators in the system, then you can hope to do well in the competition. This problem set up here for the power system scheduling is very similar to the economic unit commitment and economic dispatch problems that are solved in many of the electricity markets around the world, and is a little bit simpler in the sense that we're not considering ancillary services in these problems. And in the first phase of this problem, we're not actually considering any of the transmission constraints. We're considering a very simplified system where we're just asking competitors to consider the operating constraints of each generator in the system and to meet system demands. And that's a nice set of simplifications that make it easier for us to get started here. And then, and so ultimately in this competition, competitors are acting as hydropower fleet schedulers, and they are providing reservoir release schedules from each reservoir that is then calculated by our scoring platform to determine the hydropower generation capability offered to the electricity system. And then again, the platform will determine the power production that is dispatched to by every generator, and produces an economic and environmental benefit from the power system operations. So in that, there is a requirement that water release schedules are subject to penalties for violating water system physical and operational constraints. Physical violations are very costly in that you will get a very bad score if you violate the physical constraints, and the operational constraints are less costly in that they are penalized, but not so severely. So the goal here is to not get penalized by violating physical and operational constraints in the water system, and get incentivized to produce as much economic and environmental benefit in the power system. And we'll define exactly what those are. Okay, so this competition, a little bit about the competition in general, that the competition will essentially ask, or will provide input data to each of the phases. So the input data will describe the power system, it will describe the water system, and we'll go into some details about what the structure of that data set is in just a minute. But if you want more details, you can look at the dataset description PDF, which is included in the competitor package once you sign up on the Topcoder platform. But it also includes a power system data.json and a water system data.json, which go into details of describing the parameters of each of the generators and reservoirs and river reaches and so on and so forth. Each phase challenge problem will be driven by system size, operational horizon, and water management rules. So we will keep the same structure through each phase, but we will vary the size of the problem. We may add generators. We may add, increase the number of nodes and network size. May increase the horizon over which we're having the competition be simulated, so week to maybe a year or something like that. So the data should be complete in that you should have everything you need to solve the problem with the data that we provide. Then candidate will prepare a submission. The intention is that each candidate develops a computational approach that can solve these problems and generate and create a set of reservoir release schedules. And the other piece that is very critical in the submission is that a technical narrative is required. So we are asking competitors to provide a technical documentation of the approach that they have developed, so that we can use that to evaluate the novelty and understand the competitors' general awareness of other approaches out there and things like that. We also are asking for a summary slide that is not going to be scored, but it will be used to sort of as like a title page for the submissions once they are scored and ranked. The other piece that is not included here, or sorry, the other piece that's highlighted down here is a software submission. We do ask that if you're willing to submit your software, we would love to take a look at what's being used for the calculations, but we are not explicitly scoring that software, and it is not explicitly calculated in the score. So the prize is being offered in 3 phases of increasing complexity and increasing reward. So the first phase is well underway. I believe there's about a little over 2 weeks left in the submission window on the Topcoder platform. And then we will open phase 2 sometime in June, and then phase 3, the sort of grand prize phase, will be later this year. In total, the prizes add up to about $75K and prizes. And for each phase, we will keep the same data structure and general structure of the prize, but we will adjust the data sets that describe the power and the water systems in there. And so for right now, we have somewhat simplified problems by not providing some of the data that we've described up to now in this presentation. But we may exercise that description to provide additional data on transmission line limitations, water operational constraints, things like that. So we have laid things out in the rules document and in all of this description to give freedom to create fairly complex problems. But it is worth noting that the phase 1 problems are significantly less complex and don't include all of those details. I mentioned that the prize is actually being executed on the Topcoder platform. Here's a screenshot of the Topcoder platform. If you are interested in competing, please go register and you can make submissions on the platform. All of the information itself is available on the Topcoder platform. And then once you make submissions, you are given some feedback with some additional details that we can talk about in just a second. Okay, so a few details about submitting and getting scored and what you can expect through that process. So another review of the submission requirements. We are asking for a submission summary slide. Really, it's like a title page. The reservoir release schedule is the principal submission. This is the main piece. This is the only piece that is being scored in the automatic scoring process on the Topcoder platform. Then a technical narrative is required to get a final score and does go through a qualitative scoring process that we will conduct with several expert reviewers after the close of the competition window. So for the first phase, that's in a couple of weeks. And then the final piece is the software that we are asking folks to submit, but we will not be scoring and not be making that public. The only public piece of the submission will be the summary slide. Scoring in the quantitative scoring of the hydropower release schedule, we have broken that down into a few categories. So, sorry, there's a qualitative scoring of the technical narrative worth 30 total possible points, and then the quantitative scoring that will be automatically evaluated on the Topcoder platform is broken into a hydropower management performance score and a hydropower generation benefits score. And so this is kind of broken across the ability to respect the constraints on the river basin management and physical representation of water flow side, and then on the ability to perform well in the power system operations side. So those are worth 60 points each. And then in combination with the qualitative technical narrative score, the total possible points is 150. On the automatic evaluation side, that will evaluate the water system and power system performance, this is executed automatically on the Topcoder platform. So the gray box kind of represents the evaluation calculations. And so the submission from competitors is the reservoir release schedule time series for each hydropower facility. And that gets passed to a water system simulation that calculates the energy generation, the upper bound of energy generation from during each time period from each reservoir. That goes in two places. First, it goes to the hydropower management performance score calculation, which essentially evaluates how well the hydropower release schedule meets the river basin operation constraint and physical constraint definitions. And then in addition to that, the hydropower production that is calculated from the water simulation is passed to the power system simulation as an offer into the economic dispatch problems that are being evaluated. And that power system simulation then clears the set of optimization problems to optimally schedule power system resources and generate electricity prices and electricity dispatch signals for each generator. And those are used to calculate the hydropower generation benefits. And that's both on an economic and environmental basis. And then these are combined together to create a total quantitative score. Abby, do you want to, or sorry, this is the power system economic and environmental benefit description. So there's two elements to the power system scoring. First, the economic benefit, which is simply the electricity prices, or the LMP, the electricity prices at the locations of the hydropower resources times their scheduled hydropower production. So the total sum of this creates what we call the hydropower economic benefit, generated from each of the feasible hydropower generation schedules that comes out of the scoring platform. And then on the environmental benefit, we are calculating this as a sort of a theoretical offset of emissions from a gas turbine, a gas generator, a theoretical gas generator in the system. So we've created a benefit factor, which is clearly spelled out in the rules document. And then we, again, schedule the scheduled hydropower production times the benefit, and we sum that up over each hydropower facility, and then over the time series that the schedule represents. And then we use each of those to create these benefit metrics. And we are scaling that to have a total possible number of points of 60 points. And we normalize that by the largest power system benefit. So we take the maximum possible prices and create that as largest possible benefits. And we take a maximum possible output to create the maximum possible environmental benefit. And this, again, is spelled out in more detail in the rules document. And Abby can describe a little bit more about the water system performance score.
Sure. Yeah. So kind of like going over what we've talked about in the first water system slide, there are two types of constraint violations: the physical constraint violation, the operational constraint violation. So a physical constraint violation represents a fundamental error in accounting water, either spatially in the water system or over time throughout the simulation period. And this part of the score is heavily penalized because, you know, if you violate these physical constraints, it means the reservoir release is not physically possible. And, you know, we don't want to let that happen. And so for each reservoir in the system that you are scheduling operations for, there's an inadequate release score and an excess release score. So an inadequate release occurs if the competitor submitted release is less than the feasible release. And so this can occur if a reservoir is completely full and the competitor submitted release is too small, causing the dam to overtop. We consider that in this competition to be a physical violation of the described problem data set, and therefore penalized. On the other side, we have an excess release score. And so that occurs if the competitor submitted release is too large or greater than the feasible release. And so that can occur if, for example, a reservoir is nearing empty and the competitor submitted release is too large for that reservoir volume and other upstream inflows to support. And so that will incur that type of violation. And so for every single time step, we are checking each reservoir's operations against these two, you know, ways to violate a physical constraint. And so if any, you know, given time step causes a problem, then for that entire simulation period, that inadequate release and or excess release incurs a violation of 0. So, it's highly encouraged to follow the physical constraints. The operational constraints are scored a little bit differently because, violating an operational constraint represents an undesirable but still feasible operation. And to, adequately penalize those releases, we look at only time steps when an operational constraint is violated. So, that could be when a flooding threshold is exceeded or a fish flow is violated. And we calculate that as the average violation for those time steps. And we want to do that so that, anytime one of these constraints is violated greatly, so, if you release 0, that's a heavier penalty on your score. And so for each operational constraint, that we'll have in future phases of the competition, each operational constraint feature will be scored from 0 to 10, and that's based on the average violation score. So, and then for the whole hydropower management performance score, we scale it from 0 to 60. And so that will just depend on how many subcategories we have. Yep, so that's how the water system is scored.
Great, thank you, Abby. And then on the qualitative side, the technical narrative will be scored. There's a set of statements that we've asked the competitors to address in the technical narrative, and each statement will be scored on a 1 to 6 scale. We've provided a pretty comprehensive list of the type of content that should be provided. The total technical narrative shouldn't exceed 2,500 words and a few supporting figures. So not too enormous of a lift, but we will use this to help ourselves understand how each competitor came to the solutions that they're submitted. The release schedule itself should be provided in a comma separated value file that is structured as follows. So for each of the reservoirs that we're asking competitors to represent in the competition phase, we will ask for a column labeled accordingly. Like in this case, reservoir 1, 2, and 3. These are the names of the reservoirs that are being provided in the data. And then the schedule is in acre feet per period, and the resolution of each period should be 1 hour, and the timestamp representing the periods should be provided in this format with a column header range. So all this is laid out in the rules document, but it's nice to highlight it here. And we have clearly identified the duration of the entire competition for the number of time steps for each phase as well.